Oh shoot. Okay, Zoom was muted. Okay, lots of technical difficulties today. Okay. Okay, so sorry about that. Yeah, basically what I was saying is just that the construction of state is sort of the fundamental building block, which helps us represent our world around us. Okay, so we're going to represent our state of the world with the variable x. And at a slightly more detailed level, what we want x to capture are the elements of the world which are sufficient to predict how things are going to behave in the future. More specifically, we wanted to capture the sorts of things in the future that we want to base our decisions now off of. So we want this variable to somehow capture enough useful information to make decisions with our system. So what are some examples of state? So if you think about a robot, if I have a mobile robot moving through the world, its state might be its pose. So this is going to be its position and its orientation in the room. If I have something like a robotic arm, so my state can be the joint angles and the joint velocities of my arm. If you're trying to localize objects in the room, this can be a bit more complicated. So this can be things like dynamic objects, so objects that are moving through the world, like pedestrians in front of your car. They can take on a lot more complicated values. You can have discrete/continuous things, so trying to estimate, is there an object on this table? If so, where it is. But the point is, our notion of state can get very complicated, and you'll deal with that later in the course. Okay, so coupled with our notion of state are what we're going to call measurements of our state, and we're going to denote this with z of t. So this is a measurement that we receive at some time t. Okay, and so these come from all of our sensors on our robot, right? So for example, for our car here, it is going to be something like the LiDAR measurements we have. And sort of the sort of key thing here is that in a lot of cases, our measurements are going to exactly tell us what the state is. Okay, so one simple example, if I have a GPS measurement of where my car is, and I'm the military, so I have it up to like about an inch precision, a GPS measurement very directly tells you where your robot is in the world, right? On the other hand, so if I have a laser scan, so I'm trying to scan this room I'm in with a LiDAR on my car, my laser information might tell me sort of the relative distance between me and this chair right here, but there's an issue, right? If I am not exactly sure where this chair is in the world, then I'm not sure where I am in the world. So a lot of times these measurements that we're recording tell us relative or partial information about the world. So, this gets even harder when you use even more complex modalities to try to estimate and represent the world. So a lot of autonomous vehicles, for example, have a RGB camera, which they use to try to extract information about the quote unquote state of the world around them for things like pedestrians and these sorts of things. And it gets way more complicated to write down what state even is in those settings, and how the measurements you're taking correspond to those. Okay, so the final piece of the puzzle here is going to be what we're going to call actions. So we're going to represent this with u of t. So actions are the sorts of things that we have control of over as engineers, okay? So for example, so for this car here, my actions can be things like the throttle that I'm going to use to sort of propel my car forward, and my steering angle, which is going to control how fast I'm turning in a different direction, okay? So oftentimes you can represent these actions in different ways. So here you can sort of choose these actions somewhat abstractly, like, turn my wheel to this angle, try to drive forward with this much force. But underneath there, you're going to have a lot of lower level components in your motors, which are like actually putting, like electricity into motors and actually causing the propulsion forward. And so a lot of times we don't have to choose our actions to be all these low level details. And oftentimes choosing your action along with your state representation is really key for sort of building a model that's both useful and accurate when it makes predictions, but it's also easy to make decisions with. So yeah, again, there's a lot of different ways we can define what actions are, and we'll cover this a little bit later. Okay, So the sort of fundamental problem we're going to deal with today is we don't have access to the state of the world, right? So all of these things, which I said could be states of our system, are things that there's no real absolute true way to measure these sorts of things. We can only try to infer what these things are from the observations and actions we took. Because at the end of the day, all we have for these robotic systems are the observations we saw from our LiDAR, and we know, what actions I told my car to do. I told it to go this fast and turn this rate. I saw these relative observations of where I am compared to this chair over here. And from that, I have to somehow try to guess or infer where my robot really truly is in the world, okay? And so that is what we're going to try to do today. We're going to try to understand how we can sift through this never-ending incoming stream of observations and actions and somehow try to maintain an accurate representation of the world around us as encapsulated by our states. Okay. Any questions about the setup? This is going to be sort of what the entire lecture is about. Great. Okay, so the way we're going to write this down a little bit more formally, and the reason we care about this is all the decision making we're going to talk about later in the course depends on having some representation of your system or the world you're in and then acting upon that. So the way we're going to formalize this is with what we're going to call a belief state over the world. So what this belief notation here is saying is that, well, actually, does anyone want to take a stab at trying to explain in words what this notation might mean? Yeah.
Belief during, or the probability you're in the current state given the actions you take and the measurements you know.
Yeah, exactly. So that's exactly what we're going to try to do today. We're going to try to come up with some probabilistic representation of what we think the world is around us and where we are in that world, given this entire history of information that we've seen come in before. And so exactly like was said here, belief is a probability that we are in some given state, given everything we've seen. If you're reading different sources, your belief over different states, you might hear that called a posterior, an information state, a state of knowledge. And so a big thing you'll deal with over the next few lectures is how do you represent these distributions? This is actually one of the biggest problems in a lot of robotics is how do you concisely represent all these probability distributions in ways which can be stored with a reasonable amount of memory, lead to predictions which are easy to calculate, and a lot of other things you'll dig into later. So the next thing I just want to talk about real quick is defining what a state is really hard, and oftentimes it's going to be more of an art than a science. So for example, when I was talking about the state of the car here, which you'll be dealing with, it's probably pretty reasonable to have this be something like your position, your heading, and your forward velocity, okay? And given the sorts of situations you'll be dealing with in this class, that notion of state is very useful for making predictions about where your system is going to be in the future, okay? But this is very different than if you're someone who works on Formula One cars. And so the reason for that is these cars are traveling at hundreds of miles an hour, whipping around corners. And when people model these systems, they actually have states which are the momentum in your front left wheel, the deformation of your wheel, because these are quantities which in those situations become more important for making reasonable decisions in the future, okay? So what I'm trying to say here is that there's lots of different ways you can define state. There's lots of different things you can put into your representation of the world around you. And it's oftentimes hard, and this is really where a lot of the good engineering comes in, trying to strike a balance between putting in enough states which give you enough useful information to make decisions about how you want your system to evolve in the future, and sort of having so much information in there that it's difficult to deal with all of these variables at once in a reasonable way. Oftentimes, given the fact that we have a very limited amount of online computation on the systems that we're trying to deploy our algorithms on, And so oftentimes there's a lot of trade-offs you have to deal with when you're defining states. And then real quick, that just sort of motivation for why are we defining states with this probabilistic belief notation, or excuse me, why are we representing our states with this probabilistic belief notation? And there's a number of reasons for this. So this allows for robustness to external noise. So there's going to be lots of things happening in the world, which I don't want to sort of write down explicitly, like, wind buffeting my car and these sorts of things. Writing things down probabilistically enables you to deal with uncertainties in the world around you. If you know that you have uncertainties in your state estimation or representation, then you know that in some cases, it might be useful to actually try to go gather more information about what state you're in so that you can make more intelligent decisions in the future. We'll go through an example of this later in the course or in the lecture. Sometimes there's systems which are just inherently stochastic or uncertain. And oftentimes our sensors stuck, and they have a lot of built-in uncertainties, and we need to account for those. Okay, so this is what we're going to try to do today. We're going to say, okay, let's say we fix some notion of state. How can we estimate it given the observations that we've seen? Okay. So to do that, we're going to brush up on probability real quick. So I'm going to sort of very quickly gloss through the next couple of slides, just because they're not the most important for what we're going to be talking about today. But I think just heads up, in these slides, there's a number of sort of just useful definitions. We're not going to use them today, but if you want to brush up on probability further, it would be useful to go look at these two slides. But what we're going to really focus on today is trying to capture the probability of different events, which, for example, can be denoted by this big letter A here. Okay, so just a quick review of discrete random variables. So if we let X denote a random variable, for discrete random variables, I can take on a countable number of values. So x1, x2, x3, dot, 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 dot. These are the number of realizations or sort of states we can have our world exist in. So px or p of xi is the probability that the random variable x takes on the value xi. So P is called a probability mass function. This is our model for the probability of different events. And sort of key onto the word model because it'll be important later. So for example, if I have a mobile robot and I have a bunch of different rooms that I'm trying to estimate which room I'm in, I might have a world where my robot can be in a number of different rooms, and I might have different probabilities associated to being in each of those rooms, given the observations that I've seen. Okay, so there's a lot of there's a lot of different discrete random variables that you might have seen. You may have seen some of these, but yeah, many different discrete random variables or models of different discrete random variables. So for continuous random variables, now we're going to be in a situation where X can take on a value anywhere in some interval. So for example, this can be my position in this room. Sometimes people actually would break the room up into a number of discrete grids and try to say what grid you're in, but you can also represent this by some number, which is I'm this many meters from that wall and this many meters from that wall. So just remember, the difference between discrete and continuous random variables is continuous random variables. Now we sort of integrate everything instead of having discrete buckets that everything is lumped into. And again, there's many different types of continuous random variables, many of which you'll run into throughout this course. So multivariate Gaussians are going to be your best friend, and something you're going to deal with a lot later in this course. Okay, so state estimation is going to be built on a couple of computations, which we're going to use again and again and again. And we're just going to walk through some brief review on probability to remember what those basic computations are. Okay, so py comma x denotes the probability that both the event x and the event y happen. So we say that x and y are independent of px and py is equal to the probability of px times py. So if I flip a random coin twice, or a fair coin twice, the probability that I hit both times is equal to the probability that I get heads on the first time times heads on the second time. So probably the most important one we're going to deal with today is trying to estimate the probability of some event x, given that we saw some event y. And this is what we denote with this x/y notation here. It's the fraction of times that we're going to observe the event x, given that we had already observed y ahead of time. And sort of the important computation here, right, is this is really just the probability of x and y divided by the total number of times you're going to see y. So the total probability of y. And then, so if we have a model for the probability that we're going to see x given y, so if we know this ratio right here, then we can calculate the probability of seeing x and y if we know the total number of times that y is going to occur. Right, and so if x and y are independent, basically that means that learning any more information, knowing that y happens isn't going to be informative of whether or not x happens. And the way we formalize this is by saying that the probability of x given y is just the probability of x. So knowing y doesn't change how you would guess that x is going to happen. Okay, so the law of total probability basically just says that if I want to calculate, okay, so first it says is that all of the possibilities in the world, all of their probabilities have to sum up to 1 all of the time. So if I sum up across all the different possible instantiations of x, the probability of that has to equal 1 in the discrete case. Same thing, but you integrate in the continuous case. It also says that if I want to estimate the probability of x occurring, I can do this by marginalizing out the variable y. So what does this say? This says that if I want to estimate the probability x, I can add up all of the probabilities across all the possible different y's of p comma y, or px comma y, and this will enable me to recover the probability of x happening. And similarly, we can do this with conditioning. So if I want to estimate the probability of x happening, in the discrete case, I can add up, right, so like py times px comma y. This is the probability of x happening, given, like say, like xi happening, and I can sum up all the different ways that's going to happen. Oops. Sorry about that. Okay, so we're not going to dwell on this too much, but just to sort of run through some simple toy examples here. There's some more which I would encourage you to work through if you just need a refresher on this. So for example, let's say that I want to estimate the probability of positive x happening. So here we have 2 random variables, x and y, and they can take on positive values of positive x, positive y, and negative values, negative x and negative y. So if I want to estimate the probability that positive x is happening, if we look at this chart here, this is really just summing up all of the numbers in the column for positive x. So here positive x happens with 0.2, here positive x happens with 0.3, and I just add those up to get 0.5 is the total probability that x is going to happen. Okay. So for marginal distributions, sort of similar. This is actually just the computation we did for x. Again, if I want to calculate the probability that positive x happens, I calculate effectively what is the probability of x given positive y, and what is the probability of x given minus y. Add those two together, and I get my total probability for positive x happening. And so to calculate conditionals, what do I do? So what is the probability of positive x given positive y? So this is the probability that positive x and positive y happen. So that's going to be 0.2 on the top right column over there. And then I can divide this by the total probability that positive y is going to happen. So that's 0.2 plus 0.4. Okay. So again, I'm dividing the probability that x is going to happen with y divided by the total probability that y is going to happen. And this gives me the fraction of the time that x happens when y happens, which is positive x conditioned on positive y. Okay, so now we're going to review Bayes' formula, and this is the most important formula you want to leave remembering today, because basically all the state estimation you're going to do for the next few lectures is just doing this computation over and over and over and over and over again. Okay, so okay, so I'm using my mouse to do this a little bit more efficient. Okay, so the way we're going to derive this is by saying, using the rules we had before, we can write down the probability, the joint probability of x and y happening in two different ways. Okay, so using these two different ways. Okay, and then what we're going to say is, now I want to estimate what is the probability of x given that I saw y. Okay, and we can sort of do a little bit of algebra here and flip things over. Move this to the side of the equation. And so to try to unpack this formula, why does this make sense? So if we recall that Ex comma y is given by this formula right here. So on the left-hand side of this formula, what we're trying to estimate is the fraction of times that x occurs when y occurs. On the numerator on the right-hand side, what we're estimating is, okay, on the denominator on the right-hand side, we're estimating the total probability that y occurs. And on the numerator, that term is giving us the probability that x and y occur together. Okay, so this again gives us the fraction that x is occurring when y is occurring. Okay. Okay, so this is mostly just like a little bit of notation. Again, we can sort of write down these probabilities in different ways. So oftentimes the py term on the denominator here. So there's different ways we can calculate this by summing over the x variable in different ways. But oftentimes this fraction 1 over py, you'll see this represented with the constant eta. So that's 1 over the total probability that y can occur. And the reason people use this constant a lot of the time is because eta doesn't depend on which x is occurring. This is, so yeah, as we'll see, this constant is going to pop up in our computations when we apply Bayes' rule in the next few slides. Okay, so I think this is one of the most sort of like classical examples of Bayes' formula. And basically, it shows you how to what Bayes' formula really tells you is how you can calculate the probability of certain events given the observations that you saw. Okay, so for example, if you're trying to treat someone from cancer, right? So cancer is the possible state of the world, and we can't objectively measure whether or not someone has cancer. All we can do is take observations which might indicate whether or not they have cancer. So in this case, this is going to be our symptoms. So in this example here, there are 100,000 people. So one person in 100,000 both has symptoms and has cancer. But there's also 10 people in that 100,000 who have symptoms but don't have cancer. Maybe they have symptoms from some other cause. And so the thing I want to estimate is the total chance that someone has cancer, given the fact that I observe they have the symptoms. And the reason you want to do this is because this is whether or not they have cancer is something that you will use to make decisions about how to treat them in the future. So this is something we want to estimate. So I'm running a little bit short on time, but basically, yeah, you can run through these computations, and I'm not going to go through them. But again, the probability that we have cancer is going to be equal in the end to the probability that someone has cancer and has symptoms, which is 1, divided by the total number of times that people have symptoms. That's 1 plus 11. And that's how we end up getting this probability that you have cancer, given that you have symptoms. Okay, and so why do we use Bayes' formula? The reason for this is because effectively it allows us to sort of estimate things in a causal way. So if we go back to our example here, the thing I want to try to estimate is actually that the probability that someone has cancer given that they have symptoms. But causally, the symptoms don't cause cancer. Cancer causes the symptoms. And so in a lot of cases, we can actually build a better model for the probability that someone has cancer or someone has symptoms given that they have cancer. And so oftentimes it's just easier to estimate these things in this way using Bayes' formula. Okay. Great. So any questions on the probability review? So in the last part of the lecture, we're basically just going to arsenalize Bayes' rule and the law of total probability a lot, and we're going to try to understand how to estimate the state of our system. So any questions on the probability review? Okay. Okay, so we're going to come back now to our representation of the world and how it evolves that we built up earlier in the lecture. Okay, so the way that this works is that at some time, let's say like time t minus 1, we have some state of the world. At time t, we choose some input u, and together the previous state and our action that we take is going to determine our state at time xt. Okay. Then this time xt is going to generate some observation z of t. Right, and so again, our sort of assumption that we're going to be working with is that the robot does not know what this actual progression of states are. All we see is what's happening in the bottom row here, the UTs and ZTs. And again, we get 1 action and 1 observation per time step. Okay, so again, we want to sort of calculate okay. What we want to do is we want to calculate the probability of some state given all of the observations that we've seen. But in general, this is just completely intractable to directly calculate this probability down here. Does anyone have any thoughts on why that might be? Yeah.
Because I think for more and more states, you have to like store all that information and like use it to do this calculation of this probability here.
Yeah, exactly. Right. So if I want to predict what's going to happen when I push this cup or bottle or whatever, I probably don't need to directly condition this on what I had for dinner when I was 11 years old, right? Things which are really far in the past oftentimes don't actually actively impact how the world is going to evolve on the timescales on which we're making decisions. And so oftentimes we can ignore a lot of things what happened in the past. So the way we formalize this is with something called the Markov assumption, which is sort of a lot of the bedrock of decision-making theory that has been built up over the last few centuries. And so a little bit more formally, what the Markov assumption says is that the probability of a state T, given our history of previous observations and actions, is given to the probability if we had only observed our previous action and state. Okay. So again, what that means is when I go to push this cup, it doesn't matter what I did yesterday. All that matters is right before I make contact with it and try to push it, what is the velocity of my arm and how hard am I pushing forward? Okay. And similarly for our observations, when I'm trying to see where this bottle is, really all that matters on all that really should matter is actually where it is, what is the actual state of the cup in the world, not where was it yesterday. Okay, Markov assumption makes sense to everyone? Okay. So what we're going to do is sort of based on the Markov assumption, when we do probabilistic state estimation, we're really going to assume the existence of two key things. So the first one is a state transition probability. You'll hear me call this dynamics. You might hear this called the motion model. But really what this is our model of when I'm in a certain state at time t-1, I apply the input ut. What is the probability distribution over future states that I see? So this really captures, as I'm in different states and as I take different actions, how does my system evolve through the world? And then the second ingredient is we need a model of given different states, what is the likelihood that I will see different observations? So for example, when I'm looking at my bottle here, if I was a robot and I was doing this with LiDAR, I'll have a pretty good estimate of where it is, but LiDAR often jitters around a little bit in terms of exactly where it's estimating where things are. And so if you want to make decisions based off of those observations, you want to have an approximate model of, given where it truly is, what is the set of observations you're going to see? There's a lot of times when we can leverage the Markov assumption, and you're going to be doing this a lot throughout this class, but I think it's worthwhile just mentioning when it doesn't hold. And the basic idea is when your state doesn't capture all of the information needed to make predictions about the future. An example, okay, so if we go back to the car example I used earlier, if I have an F1 car and I don't model the tires, I am not going to be able to accurately predict where my car is going to go in the future. So that's a case where there's a state of the world, which I need to write down in order to make accurate predictions. So if I'm trying to estimate where a pedestrian that I see with my autonomous vehicle is going to be 3 seconds from now, well, I don't know what's going on inside the pedestrian's head. There's states, if you can call them that, inside the pedestrian's head, which I can't measure, which I don't have access to. And so it's very difficult to make accurate predictions about how the pedestrian is going to move in the future. Similarly, if I design my model, assuming that randomly my car is going to be buffeted by wind every now and then, but all of a sudden I'm in the middle of a hurricane, there's a new state of the world which is affecting my system, which I didn't model, and now my dynamics model is going to give me garbage estimates of where my system is going to be in the future. Okay. So again, what we're going to try to understand is, given this long sequence of really long sequence of estimates and actions, how can we recursively come up with a distribution or a belief for the states that we're in at a particular time? And this is the Bayesian filter and what we're going to try to focus on today. Okay, and so the idea is we're going to apply our Markov assumption and our models for the dynamics and our models for the observations to try to come up with sensible estimates for for a distribution of how our states evolve over time. Okay, so this works recursively. So when you start at time 0, for example, you have to instantiate some initial belief for where your states are in the world. But that every time we are going to recursively do the following computation. So at time t minus 1, we have some belief over where our car is in the world. Might be a little bit hard to see, but there's sort of like a distribution of different poses that the car has here. And then what we're going to do is, because we're using the Markov assumption, we're assuming that all of the information about our past observations is captured in this distribution of beliefs at time t plus 1. So then what I'm going to do is I'm going to use the law of total probability to try to predict the distribution of where my cars should be in the future, given the action ut that I took and my prior distribution. So what I'm doing here is I'm effectively taking my previous distribution, I'm shoving it through my dynamics model. So I'm saying if I had this distribution of states at time t minus 1, after I iterate my dynamics, so I take one step forward in my dynamics, where would the distribution of cars be? And then what happens is, in reality, I apply my action, my system actually evolves and actually ends up in one of these states. So let's say that I end up in this state ZT here. So my system is going to generate observations. So for example, my LiDAR might run into this obstacle here, and basically, then what we're going to do is we're going to use Bayes' rule to try to predict the likelihood of the state we're in, we actually ended up in, given the observation that we saw. Okay, so when we apply Bayes' rule here, what ends up happening is that, so if you look at these cars down here, they're pointed away from the obstacle, and so they're not going to observe the LiDAR impacting the obstacle. And so those states are going to be very unlikely given the observation that we saw, because if we were in those states, we wouldn't have seen the obstacle in front of us. In contrast, this actual state Z here is going to be very likely because it's going to correspond very tightly to the observations of the obstacle that we saw. And this state here will be also very likely, but not as likely because it produced a set of observations that are a little bit off. So intuitively, the way you want to think about this is that what applying Bayes' rule is doing here, what Bayes' rule is doing here is we have this set of possible states we think the car will be in. And then when we apply Bayes' rule with our observation model, it's sort of upweighting states which are consistent with the measurements we saw, and downweighting states which are inconsistent with the observations that we saw. Okay, so in a nutshell, again, this is sort of what's happening here. So because we're applying the Markov property, we're assuming that every time I do this and get a new distribution over beliefs of my states, I can throw away my observations I saw at time t and entirely encapsulate all of my future predictions in my belief at time xt plus 1. And again, the way we do this is we, given our current distribution, we calculate a distribution over worlds in the future, and then we try to ground that in the observations we saw to estimate the likelihood of these different worlds given our observations. Yeah, any questions here? Okay, so again, this is a really, really powerful tool. You're going to see a lot of different instantiations of Bayesian filtering over the next few lectures. But I think like really make sure you understand this concept and what's going on, because a lot is going to build on it throughout the course. Okay, so let's go through a quick example, and I think we'll go through this. Okay, we ended like right at 2:20, right? That's the end time. Okay, we'll take our time with this, and there's a few comments on the end, and we'll get to those if we can. Okay, so let's suppose that we have this. Suppose we're at Boston Dynamics, and we have this robot Spot over here. And we are trying to estimate whether or not this door we're trying to open is open or closed. Okay, so there's two states of the world. One is open and one is closed, which we'll denote with O and C. And you have two actions at every time. So what you can do is you can try to pull the door open, or you can leave. And we have some model. Maybe we estimated this with all the prior times that we tried to open the door, and we saw the success rate of it. But we have some model P of the which gives us the probability that the door will be open or closed given our current state and our action. So, for example, let's say that the probability that the door is open in the future, given that it's closed, and I try to pull, is 0.7. So there's a 70% chance I'll succeed in opening the door. And what that means is that there's a 30% chance that I'll fail. Right, and so like intuitively, why are we doing this? The reason is just that okay, I'll let you watch the robot video on your own, but it doesn't always succeed. So oftentimes we have to actually estimate the chance that we succeeded for these sorts of things. Okay, so I can write out all of the probability distributions for my system in matrix form like this. And so on the left here, this is going to be the probability distribution. Yeah. Oops, sorry. Okay. Okay. So I'm writing out a matrix here with a probability distribution given so on the left here is the probability of states I'll see in the world, given that I try to pull it. On the left is the probability of states given that I'm going to try to leave. So we have an observation for okay, so we have an observation for how the door is going to, what are the chances are that the door is going to be open or closed in the future, given whether or not it's open or closed. And these are going to be a vector. Okay, and so let's just run through these computations. So let's say we're going to try to actually pull the door. So these matrices that we wrote down before, these are going to, we wrote them down in matrix form. And because we wrote them down in matrix form, if you actually go and sort of take the time and look at these equations, we can actually end up writing our predicted belief of where we're going to be after iterating the dynamics with this matrix multiplication. We're doing this example just because this is going to form the foundation for the Kalman filter, which you'll see in upcoming lectures. So we can iteratively run this matrix computation to give us our beliefs at what time step into the future. We can do the same thing for closed, and yeah, we can do the same thing for closed. And okay, I'm running out of time, so I'll let you guys work through the computations, but basically I would really advise that you take the time to run through these examples. I'm sorry that I didn't have time to get through them. But there's another example which I think would be very helpful for you to run through. And there's a few more concepts which Abhishek will cover at the end or next lecture. But as you're packing up, let me just remind you, this is sort of where we are in the class. Today, we talked about how we can recursively estimate states, and that's going to be the basis for everything you do in the future. Cool. And I'm happy to stick around outside if anyone has any questions, especially since we were rushed a bit there at the end. And thank you.